Hi, my name is Tim, and in this video I'd like to give a brief demonstration of Marlon. Marlon, it stands for Multi-Agent Reinforcement Learning on Networks, and it is a domain-specific language to use multi-agent reinforcement learning, or MARL for short, to make use of MARL to solve problems within distributed systems. Now, the idea is that experts within the domain of MARL can develop their algorithms without having to worry about the intricacies of distributed systems. Likewise, from the perspective of the people who develop distributed systems, they can develop their system as they're used to and make use of MARL algorithms without having to know the intricacies of machine learning. One more thing I'd like to mention is that Marlon is implemented on top of an existing language called Elixir, which is a language that is meant for building large and scalable distributed applications. To demonstrate Marlon, we're going to use a load balancing example. Here, the idea is that the master node in the network, the master node would like to distribute a particular job over a list of worker nodes. What happens is that first the worker requests a chunk of work, and it can request a small chunk or a large one or something in between. So the worker requests a chunk. Step 2 is that the master sends this chunk, the worker processes the chunk, and the results are finally returned to the master. So this whole cycle repeats itself until the whole job is finished. What I should point out as well is that the master can only handle one request at a time, so sometimes workers will have to wait. Workers can join or leave the system at any time. Some of the workers are faster than others, so they can be running on different types of machines. Finally, where does MARL come into play? Well, the goal of this example is that we use MARL to optimize the chunk size. To optimize the chunk size of each worker individually, but they're all trying to coordinate to optimize the whole system such that it runs as fast as possible. In other words, such that the workers are not being idle. Okay, so let's show our system in action. Let me open up the visualization. There we go. And next I will start up a master node and a worker node. And let me go back to the master to initiate the whole system. There we go. So over here you can see the network structure, and down here is a timeline where you can see the activity of all nodes. So over here you can see a worker node. The first thing it did is request a chunk. The master sends this chunk, so this is all the yellow parts, is just sending and receiving data. The red parts are the worker that's processing a chunk. So first request a chunk, then process a chunk, and then the whole cycle repeats itself. Now let me show you that you can just add a few additional workers. So you can see the whole system continues to run just fine. I can even crash one of the nodes and it disappears, but the system just keeps on going. One final thing I'd like to point out here is that the processing time, so the red parts, they're not always the same length. Like this, you can see that the MARL algorithm is experimenting behind the scenes with different chunk sizes. Okay, so that's a quick demonstration. Now let's have a quick look at the code itself. So this is a slightly simplified version of the whole system, in the sense that this does not contain the code that links to the visualization that I just showed. But apart from that, this is the whole load balancing system right here. Now, when writing Marlon code, you implement the environment, so the distributed system. The distributed system is represented using actors. We're using the actor concurrency model. So for instance, over here you can see an actor for initiating the whole system. You can see an actor definition for the workers. You can see an actor definition for the master. Now, when you look at the syntax of an actor, it looks quite familiar. It looks similar to a class definition. In fact, this function right here is the constructor of an actor, or this right here looks like a method definition. So it all looks quite familiar. Now, the big difference between an object from object-oriented programming and an actor is that each actor is running in its own thread. And how do these actors communicate with each other? They do this by sending messages. And usually, these messages are handled asynchronously. So this is the big difference. All the actors are running in their own thread, and they're usually talking to each other in an asynchronous manner. So when you send a start message, this is the body of code that's get handled. Okay, so this is just a quick introduction to the notion of an actor. I'm not going to go through all the details of this example. It's just highlighting the concepts of Marlon. So actors are used to represent the distributed system. Now, to specify the problem that you'd like to solve with multi-agent reinforcement learning, to specify this problem, you make use of this def goal construct. So this specifies everything you need to achieve a specific goal. In this case, we'd like to optimize the chunk size of our workers. So all we need to specify is which Marl algorithm are we using, what are the parameters that we're using, what is the action space, and what is the reward function. Now, a few things I'd like to point out is this Marl algorithm. I can show you the implementation of it. Actually, this is only a very thin wrapper around an existing algorithm. You can see here that this is just an implementation of an API that we provide. And in the implementation, you can see that all that happens is we're calling out to a Python script. So the idea of Marlon is not to directly write your Marl algorithms. The idea is that we can easily integrate existing Marl algorithms. Okay. Another thing I'd like to point out here is that this right here is the definition of our action space. And in Marlon, actions always correspond to sending a message. An action is always sending a message. In this case, the action space consists of either sending a process chunk message with parameter value 1, or sending a process chunk message with parameter value 2, or sending process chunk with 3. So all we've specified here is that the Marl algorithm can choose this parameter value of the process chunk message. Now, in general, you can make a much bigger action space with multiple types of messages with multiple parameter values. But in this case, we can only choose between a chunk size, really, that's what it represents, between a chunk size of 1, 2, or 3. Okay, so that's how you specify a Marl problem. Now, this in itself is not going to do anything. What you still need to specify is how this problem specification is going to integrate with all the actors. And for this, we provide 3 types of instructions. One is an instruction to attach an agent. So here's an instruction to attach an agent to one of the workers. And we also specify that this agent has to respect a specific problem specification. So this is our chunk size goal that we defined right here. So this is one type of instruction. Another type of instruction is do action. So when an actor uses this instruction, it tells its associated agent to choose and do an action. So by putting this instruction here, you're telling the Marl algorithm to choose an action, in this case to choose a chunk size and to send this process chunk message. So this is what happens when you make use of the do action instruction. And a final instruction would be update reward. So as soon as your distributed system has enough information to compute a reward, you can just call the update reward instruction and inform the Marl algorithm of the new reward value. And by calling this instruction, all you're really doing is executing the reward function that you provide here in the problem definition. So this concludes our demonstration of Marlon. I gave you a quick overview of how to implement a distributed system using actors, how to specify a problem to be solved by a Marl algorithm, and how to integrate this Marl problem specification with the distributed system. So that's it. Thank you for watching.